Now then, lecture 3. So, everybody ready? Everybody ready? Man the fluffy hat? Man the green fluffy hat? No? You ready? Yeah? Okay. It was you. Right, so welcome to this third lecture on computer programming with MATLAB. And this lecture is entitled 2D Arrays and Advanced Plotting. So we're basically going to pick up from what we were doing last week on arrays, and we're going to extend these arrays from 1D arrays to 2D arrays. So just come in and sit down as quickly as possible, guys. Don't worry about the notes. Right, so here's an overview of today's lecture. I'm going to discuss with you firstly the coursework. Can you just settle down? Sorry, it just makes my life infinitely harder if you try and chat over me. So first thing, we're going to discuss the coursework. And I've had quite a few questions about coursework. How do I hand it in? What format do I want? What will get me full marks? I'm going to answer all those questions now. And I'm going to then give an overview of last lecture. Then we're going to look at editing 1D arrays. So we're just going to polish off 1D arrays. There's a few little bits and bobs you've got to know before we leave the topic. And then we're going to look at 2D arrays. So this is like adding another dimension to the arrays. And then we're going to look at some advanced plotting. So what do I want from the coursework? When you hand in your coursework, what will get you 100%? So the way I want you to hand in the coursework is I'd like you to make one .m file for each question. So there's like 7 MATLAB questions, or 6, I can't remember. And I want one .m file for each question. And there's a flow diagram I think I've got you to draw. And I'd like this as a PDF. And then I'd like all these zipped together in a zip file called, so in my case, Roderick_Mackenzie student ID number.zip. And I'd like that uploaded to Moodle. And I haven't yet put the upload link for Moodle, because if I put it too early, people sort of upload stuff and say, oh, I haven't quite finished, can I edit it? So I'm going to put the upload link much closer to hand-in date, which is, I think, first few days of November, it'll say on the portal. Now, please give us a zip file. Don't give us any other random format of archive like RAR, GZ7, because these poor demonstrators have got to actually go and open this. So if you zip it up in something crazy, they're just going to have to do more work. Same with the PDF. I specify PDF because, if you send me a PowerPoint slide, they might not have the same PowerPoint version of you, and your diagram might be completely muddled up. So send a PDF, and then you'll get your full marks. So I said everybody gets about 80% in the first coursework, 70, 80%. And part of the reason for this is I give you the answer. So this is the answer to question 1, okay? This will get you 100% for question 1. So let's see what it is. It starts off with my name and my email address. This is very important for feedback. The other thing is, make sure you follow this name convention, because if you call it like coursework, and then coursework.zip, and then somebody else uploads coursework.zip, it'll overwrite their work, or your work will be overwritten. So it's very important to make sure you've got your name in the title. And then literally, all I want is just a script that just does what we ask you to do. I don't want any output, I don't want any screenshots, I don't want any, it's in the notes, you don't need to, it's actually on the internet, you don't need to take pictures of it. It's like, I've not cut it out of the notes. And then I suggest, I've said put comments in. And I suggest about a comment every 5 lines, just to tell the programmer, tell the reader what's going on. So the marking scheme is basically the demonstrator opens it, copies and pastes it into MATLAB, clicks run. If it produces the correct results, you get 80%. He then has another look at the file and says, oh, well, there's some comments. Yes, you get the rest of the 20%. So he doesn't even look at the mark scheme if it runs. And works. If it doesn't run or it doesn't do it properly, then he starts looking at the mark scheme and looks where to deduct marks. So if it runs, 100% with comments. Yeah? Any questions? It's pretty clear, pretty easy, straightforward. Yeah? Okay, if there are any questions, I'll be in the examples class later. Right, overview of last lecture. So last lecture, I told you all about complex numbers. And I said in MATLAB, it's incredibly easy to do complex numbers. All you need to remember is, you remember this I is for a complex number, just like in mathematics. Some engineers use J. I don't know if that works in MATLAB. I'll stick with I. So if you want to define a complex number A, you just go A equals 7 plus I, done. And then all these other operators you've learnt, so raise to the power, plus, minus, divide, they all work with complex numbers. And the point is now, as long as you can type the equation into MATLAB with a complex number, it will do the work for you. So you don't need to think when doing complex numbers anymore. It will do all the hard grind for you. And then we looked at this rather silly example, and I talked about variables and arrays, and I introduced you to the concept of arrays, or one-dimensional arrays. And I said, imagine you wanted to calculate the marks of 10 students. One way to do it, or a rather long-winded way to do it, would be to define 10 different variables, so in this case mark 1, mark 2, mark 3, mark 4, mark 5, etc., all the way up to mark 10, and store, for example, the average marks of the students in those variables, then go divide by 10, and then that would give you the answer. So in each variable, you've stored an individual piece of information. I said this is getting a bit boring, or it's a bit hard work if you've got 10 variables, but imagine you've got maybe 1 million pieces of data, or I think what we had last week with that music file was about 12 million pieces of data. This way of handling data just doesn't work. So I said, what we need to do is we need like a more sophisticated and sort of easier way to do this. And this is called arrays. And I said, arrays are just like a variable, except they store basically a list of numbers rather than just a single number. So for example, we could define the array of student marks as, so imagine we wanted to store all these student marks, so 72, 40, 50, 80, 60. We could just store these in this single array, student marks, by going student marks equals, open square bracket, so it's a square bracket, you've just got to remember that, then the numbers you want to store, so 72, 40, 50, 80, 60, close square brackets, and you've done it. You've defined a 1D array. Easy. I then said, very often in engineering, you need an array that counts up. So for example, you might be taking a measurement every second, and you might want to go, you might want an array that starts at time at 0 and counts up to 1 million. And it's a lot of work if you just type these in by hand. So MATLAB's got a nice automated way to do it, and it's called linspace. So imagine you wanted to define this array, time in seconds equals 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way to 14. A quicker way to do this would be to use the linspace command, and you'd go time in seconds equals linspace. 0 is the value at which the array starts, 14 is the value at which the array stops, and 15 is a number of numbers in the array. And of course, because we're counting from 0 to 14, there's actually 15 numbers, because 0 is also a number. So that's why we've got 15 there. And the final thing we looked at was loading data from files, and we looked at those cool examples of loading music, and we learned about the load command, which can basically take a whole list of numbers from a file, which could be music, it could be, I don't know, any statistics, any data you're interested in, and it will load it into a 1D array. So load, open round brackets, single quote, MATLAB music file.dat, and it will load it into an array. How much more? So this is the final recap slide. The final thing we learned about was the sound command. And we said, well, once we've got an array, let's do something interesting with it. So let's just send it to the sound card. And we can do that with a sound command, and the computer will literally take a whole array and shove it to the sound card. And the one thing that's difficult about this, or not difficult, but you've just got to remember, is that you need always to specify how many pieces of data from your array the computer sends to the sound card every second. And I said this number, 44,100, is a very special number, because that's the speed at which CDs, so CD quality music, takes bytes in an array and sends it to the sound card. So if you're sending 44,100 bytes a second to the sound card, it's CD quality music. So that's a good number to remember. Any questions on last lecture? Good? Me? Okay. How far did you get with the example sheet in last example class? How many people finished it? How many people got about halfway through? Yeah? Okay. Don't worry if you didn't get all the way through it. So I expect people to do about 60% maybe in the examples class, 50%. So don't worry. And anything you don't do, use for revision or mop it up on the weekend or something like that. So don't be worried if you're not making quick progress. It's a very, very personal thing. Okay. Now then, I just want to finish off 1D arrays now. So updating and editing 1D arrays. Now, very often, you might have your computer collecting data from, say, this jet engine here, and it might be monitoring lots of sensors. And sensor data, you'll have an array holding the temperature data from the sensors of this jet engine. So here we've got temperature equals 20, 30, 20, 90, 20. And you can imagine each one of these pieces of data could represent a thermometer at different places in this jet engine. And Then you might get a new piece of data from the sensor sent to your computer, and you might need to store this piece of data. And to store this piece of data, you want to just update one element in this array. So imagine you've just ignited the engine, and all of a sudden, your sensors send you like an updated value of temperature of the engine. And at this place in the array here, 90, you all of a sudden need to change this value 90 to the value of 1,000 because you've just lit your gas turbine. So we need some way to update arrays and like manipulate bytes in arrays. And this is what we're going to learn about now. So we're going to learn about how to change like this value or any given value to a different value in an array. So how do we go about doing this? Firstly, we've got to remember what I told you last week about how arrays are indexed. So any array, so if we look at this array here, so we've got 20, 30, 20, 90, 20, each element in this array has an index. And the very first element is at position 1. This is at position 2, position 3, position 4, position 5. So the index always starts off at 1 and then goes to the number of elements in the array. It's pretty simple. Now, if you wanted to change the fourth element of this array, so 1, 2, 3, 4, which is a 90, to 1,000, which is the new temperature data you've got, this is how you do it. You'd go temperature, open round brackets, 4, which is the fourth element in this array, equals 1,000. And the result would be your array temperature would be updated, and it would go temperature equals 20, 30, 20, 1,000, 20. So we've replaced the element in the array. So now we can manipulate arrays on really the sort of the bytes level. So imagine now our engine's getting hotter, and we get more temperature data from our system, and the computer needs to update the value of temperature in its stored array. So imagine now we need to change this second value in the array, which is a 30, to 2,000. All we'd do is we'd go temperature, this is the name of the array, open round brackets, 2, because we want to update the second element in the array, close round brackets, equals 2,000. And all of a sudden, we've got temperature equals 20, 2,000, 20, 1,000, 20. And now we can update any element in an array. The final thing I want to tell you about 1D arrays before we leave them, we'll come back to this in a more complex form at the back end of the lecture, is how to read a single element from the array. So imagine, for example, this time maybe it's not a jet engine. Maybe you're taking, maybe you're recording temperature values every day of the week. Who is that guilty person? I think it's him. I might be wrong though. Okay, so imagine you want to extract just a single element from an array. And this might be, for example, imagine you're recording temperature values every day of the week. And you say, you know, temperature on Monday is 20 degrees, temperature on Thursday or Tuesday is 30 degrees, Wednesday 40 degrees or whatever. And you want to say, what was the temperature on Sunday? What's the temperature value in the 7th element of my array? And you can extract just this single one value from an array very, very simply. All you do is you go, type the name of the array, so temperature, this is the name of this array, open round brackets, and then the index of the item of the array you want to get. So if you want to get the 1, 2, 3, 4, 5, 6, 7th element in the array, just go open round brackets, 7, close round brackets, and it'll print 20. Okay? If you want to get the 4th element from the array, so 1, 2, 3, 4, just go temperature, open round brackets, 4, close round brackets, and you can extract any element from the array you want. So now we can write anything to the array we want, and we can read anything from the array we want. And this might seem a bit dry and a bit technical at the moment, but this is one of the very, very useful things you'll be able to do, because now you can this is like the basics for manipulating any data. So you can sort data, you can now start to use this in a few lectures to average data, you can really manipulate any data on the byte level. And we'll come back to this again and again. How are we doing for time? Ages. Any questions on that? Yeah, go for it.
Does it work on linspace as well?
Yeah. So it'll work on. So sorry, I'll repeat the question. The question was, does it work on linspace too? Yeah, absolutely. So it works on any array. So and we're going to extend this in a moment to even 2D arrays, and we'll be able to chop 2D sections out of it. Okay. Any other questions? Good question. Thank you. And thanks for asking the question. Yeah. All right. Let's crack on. So until now. We've done 1D arrays. So these are super useful for things like stock market data, prices of gold over time, temperature. Guys, if you've got a question, shout it. You all right? Yeah? Okay. You know, any lists. So we can do lists. We can handle lists of data and audio data up till now. But very often, the list of, or the type of information you're handling isn't a list, or it can't very easily be formed into a list. Now, examples of this is this satellite, is this telescope image of some galaxies far, far away. Now, you all know what a pixel is? Yeah? You all know what a pixel is? Okay, I'll explain anyway. So if you look at this, so this is a picture basically of some galaxies. And what makes it up are little dots that represent the tiny little square of light. And along this axis, there's 3,000 pixels, and along this axis, there's another 3,000 elements. And this is just like little squares of light that basically are used to make up a picture. And if we zoom in on a star, so this is a star we can see here, if we zoom in, we can actually see the individual pixels. And you know there's probably 10 pixels along here and maybe, say, 20 pixels along there. And the way images, or all images, are stored on computers, so not JPEGs, but if you save like a bitmap or a PNG file, they're stored like this in a sort of very simple way. It's literally a 2D map of light intensities. And the higher the number in the file, the whiter the light. So I don't know if you can see this, but I've tried to represent this star in sort of a 2D array of numbers. And in the center, we've got very, very white pixels, right? And in this particular way this image is stored, white pixels are represented with a 10. So that's like the brightest it can be. So in the center of this image, we've got like 8, 8, 8, 9, 8, 8, 8, 8, 8. Around the edge of this star, you can see we've got basically pretty much black pixels, so pretty dark pixels. And you can see we've got 1, 2, 3, 1, 1, 1. So very low numbers representing dark pixels where there's no light. And so you can basically represent this whole image using a big sort of 2D, you think of it as a matrix effectively, of numbers. And this, in computer programming, sort of a big square matrix of numbers is called a 2D array. And that's what we're going to look at now. So I thought we'd just look at some other examples of 2D arrays or data that you might be processing. So, you know, obvious examples that you might just make yourself with your phone are pictures. So here we've got some black and white or grayscale images. These can be represented just as 2D arrays, just like that, as just a square of numbers, basically. Other examples of 2D arrays might be, so this 2D map, so okay, the world is round, but it's been projected onto like a 2D plane, this 2D map of rise in temperature, or predicted rise in temperature through global warming, if we all carry on driving those VW cars. And on the right, what country is that? This is a stupid question. US, right? Now, this is a trap question. That was an easy question. This is 2D data from a weather radar. So this is like a radar image of the whole weather radar of the whole of the United States. Now, this is a trap question. What do you think it's showing? Can you guess? What do you think that's a picture of? I'll tell you. Anybody want to guess? No? It's not weather. It's sunrise. Basically, what you're looking at is sunrise over the US with weather radar. And as the sun comes up, all the birds flock and start flying in the sky. And all these plumes here are actually birds flocking. So that's quite cool, isn't it? So that's an example of 2D data too. So, how do we make 2D arrays in MATLAB? Well, it's incredibly easy. If we can do 1D arrays, we can do 2D arrays. The trick is, all you've got to remember is this semicolon, okay? So if we've got an array called numbers, a 1D array called numbers, and it goes 9876543321, 9876543321. I can hear somebody talking really loud at the back. Thank you. If you want to make it into a 2D array, you just separate, you basically break it with this semicolon. So if we wanted to go 987, new line, we just go 987, semicolon, which means like a new line. Then 654, 654, semicolon, then 321, 321. And you see we can basically just put a new line in our 1D array and make it into a 2D array. Okay? I'll do another example. So imagine we want to make the array 1, 1, 1, 2, 2, 2, 3, 3, 3. We can make this by just using a semicolon. So we go A equals, open square brackets, just like you did for your 1D array, 1, 1, 1, semicolon, 2, 2, 2, semicolon, 3, 3, 3, close round bracket. Yeah? And final example, I know I'm labouring the point a bit, but I want to make sure everybody's got this before we leave. If you want to make the array 7, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, etc., you just go A equals, open square brackets, 7, 2, 3, 4, semicolon, meaning the new line, 5, 6, 7, 8, semicolon, meaning the new line, 9, 10, 11, 12, semicolon, meaning the new line, etc. Yeah, everybody got that? Yeah, good. Right, so that's also a bit laborious. You've actually got to type in the array by hand. So I'm now going to show you some quick ways to generate big arrays with zero work, okay? So the first good method to calculate 2D arrays is the zeros command. Now, very often in engineering, you might, for example, start your program, and you might know you're going to receive a kilobyte of data. So you need to define some basic memory to store this kilobyte of data before it comes in from your sensors. And a good way to do this is with the zeros command. And it literally makes a square 2D array. So if you want an array of zeros filled with, of size 4, so 1, 2, 3, 4, 1, 2, 3, 4, you just type A equals zeros, 4, 4, and you get a 4 by 4 matrix or array of zeros. And it works for any size. And if you actually replace the 2 with a 1 here, you can actually make a 1D array of zeros. Any questions about that? Okay. Good. The other quite cool command is the rand command. And very often, for example, imagine you're trying to generate white noise to test some type of system, or overlay white noise on some audio data, or something like that. Or you can also use it to predict, for example, poker games. So you can do, it's called Monte Carlo simulation, where you pick random numbers with the computer and see who's going to win the poker game, or what your best hand is. So random numbers are very important in engineering. And a good way to make big arrays of random data is with this rand command. And if you want a 2 by 2 array of random numbers, you just go A equals rand 2, 2, 2D array of random numbers. Or if you want a 2 by 3 array, A equals rand 2, 2. Now, do I have time to tell you about random numbers? I do. Right, so I'm just going to give you a quick tip on random numbers. Computers, so this won't be an exam, this is just like good knowledge for you to have. Computers are not random. They do not do random things. When you turn them on, they always do exactly the same thing. And they're completely predictable. Therefore, random numbers on computers are very difficult to generate. And if the computer's giving you like a random number, it's not usually a random number. Often, they start like the random selection process by taking the time or something like that, or the day of the week, or something like that. So very often, if you switch on 2 computers at the same time and ask them both for a random number, they will very often give you the same random number, okay? So just watch this. When you will come across this at some point, you'll be like, why is that doing that? And it's like, well, because it's not random. So that's just a tip. Right, let's watch a video about these arrays. It's not a very good, well, it's not a very long video. Pop. Right, here we go. Okay, so let's just go right from the beginning. So making 1D array, 1, 2, 3, 4, 5, 6, 7, 8, 9. That's a nice 1D array. Now let's make it into a 2D array by popping in those semicolons. Bang, easy. Let's do another example. I can't actually remember what I typed because I typed this a year ago. So we're making another 1D array. And we're going to make this into another 2D array just by popping in semicolons. Okay, see how easy it is. There's nothing really that's too difficult. Now let's make an array of zeros. So I've got to define the variables. C equals zeros. 2 by 2 array of zeros. 4 by 4 array of zeros. Yeah, then I think we get silly at some point. 1,000 by 1,000, I think. So that's a huge array of zeros just defined like that. Much quicker than typing it in. I think we're now going for random numbers. 2 by 2 array of random numbers. 4 by 4 array of random numbers. Get the idea? Yeah? And we can go as big as we want. Okay. So that was the demo on 2D matrices. So you can now do 1D and 2D matrices quite easy. There we go, lots of random numbers. Right. Let's pause that. Presentation. What's up next? Right. Now then, just like with 1D arrays, I said it's often a real pain to type them in or to define them with mathematical commands or what have you. And very often you want to take your data from a file which you've stored from a measurement system or something. And I told you last lecture that we can load 1D data from a text file. So if we've got a list of numbers, we just go y equals load my data, hit return, it loads it all in. It's exactly the same with a 2D array. So if you've got 2D data stored in a file, literally just as text, so if you've got a notepad file or something like that, and you go load my data.dat, you can just load this in straight into a 2D array. So now we can pull 2D arrays from disk. So let's look at some real 2D arrays. This is where it gets quite interesting. So there's been this satellite called the Mars Global Surveyor, and I think it's a NASA one, or it might be NASA joint ESA, not sure. And it's been surveying the surface of Mars since 1996. It's literally been flying around Mars, mapping it. So we've got a very, very detailed map of Mars now. And we know how high all the mountains are, how deep all the valleys are. So now we know where to land spaceships, which is very handy. And it's produced a very detailed map of the Martian surface, which you can download from NASA. So you're used to looking at sort of 2D maps of the Earth's surface like this. So here's Earth as a ball, but it's been projected onto a 2D surface. And if you go to the NASA website, you can actually download, I've sort of simplified it here, their data set's huge, it's gigabytes, so I've sort of simplified it. In principle, you can download a file called marsheightdata.dat, which is a 2D data set containing basically all the height profile data of Mars. And this is the format this marsheightdata.dat comes in. I've shrunk it down a bit, so it's sort of easy to handle in a lecture. And in this file, we've got 1,024 points across the x-axis and 501 points across the y-axis. So we've got, whatever those numbers are times together data points. So how do we load this file into MATLAB? What command would we use? Load, yeah, exactly. It's not difficult. Load. So just load marsheightdata.dat, and instantly we get the array in MATLAB. Now then, I want to teach you a new command. We learned about the plot command, I think, in lecture 1 or 2. And this is very good to plot 1D data sets, so sine waves or stuff like that. If you want to plot 2D data, you need to use the surf command. And you can think of it because if you imagine you've got some 2D data, you've got like a surface, and the 2D data produces like a contour surface. You want to plot the surface, so therefore it's surf. So to plot 3D data, or 2D data, all you do is you load it in, like that, then you go surf data, and let's look at the results. And this is what it looks like. It looks quite cool. So this window just pops up in MATLAB. And if we look at the axes, we've got 0 here, 500 here, 0 here, 1,000 here. So all the points are basically positions in the array. Yeah, and we can also, if you get that, can you see this tool here? If you click on that with a mouse, you can drag this image around, so you can sort of just fly around it in 3D, and you can position it so it looks like a 2D map of the Martian surface. What else? Yeah, the final thing I want to show you is this color bar. So you know when you make, or you've seen in magazines or journals or whatever, 3D plots, very often on the side they have a nice little color bar like this. So it'll go from deep blue to deep red. And I don't know, if you're looking at global warming or something like that, the very bottom value will be sort of 0 degrees and the top value will be like 4 degrees or something. Well, in this case, it's basically height data. So, and the command to put this on, by the way, is color bar. Color bar is spelt wrong, obviously, because it's American. But yeah, that's what you type. And it's important which order you type these in. So you need to go surf color bar. And sometimes you get the color bar but not the picture, or the picture and not the color bar. Just try different iterations and it'll work. So let's have a look at this Martian data. Oh yeah, how deep's this crater here? Can you see? How deep's that? Huh? I heard the right answer there somewhere. It's an 8 kilometer deep crater. 8 kilometers. Can you imagine that? If you fell into that, you'd fall for like 3 minutes before you met your fate. Okay, so let's watch this video. Right, so let's load in the Martian height data. Now, wow. Notice this, guys. Notice this semicolon here. I didn't tell you about this, but it's in the example sheets. I'll tell you about the example sheets. If you've got a load of data, like streams of data go to load in, MATLAB by default prints everything to the screen, and it takes ages. If you want to speed up the loading of something and stop it printing out streams of data, just put a semicolon at the end, and it won't print anything. The command's still executed, but it just won't print anything. And it's very useful, that. So let's watch this. So it's loading. It's quite a big file, or maybe I've just not pressed play. I'm going to have to start again. This is irritating. Sorry. Boom. There we go. Right. So we load in the Mars height data, or the profile data. Takes a second to load. And if we just type the variable name, it will print it all out. So there's loads of data there we just loaded in. And we just go surf A. Now then, I think I make it bigger. Now, it looks a bit odd. Now, the reason it looks a bit odd, I'll tell you. By default, the surf command, when you've got like multiple points, what it does is it does the nice 3D plot, but then it joins each point in the mesh with a black line. Okay, so it looks quite nice, like having black lines between mesh points. If you've got maybe a 10 by 10 graph, but if you've got a 1,000 by 500 graph, there's so many black lines between so many points. It just looks like a sea of blackness, and it doesn't look very nice. And there's a command to turn this off. Now, I wouldn't expect you to remember this. You're about to see it. I wouldn't expect you to remember this command to turn off this sea of blackness. But all I'd say is that if you remember back to the first lecture, and I said, nobody looks in the help to solve their problems. I had this problem. I was like, oh, this doesn't look very nice. What do I do? Looked in the help, and there was like an obvious, it just said, do this, and it will solve your problem. So always look in the help if something's not going quite right. So if I can start it. Yeah, here we go. So there's a bit more flying around. So let's get rid of that, because it looks ugly. So if we put into the surf command, edge color, none. Now, I would not expect you to remember that in an exam, but the message is just look at the help if you get stuck. And look how much prettier that looks just by tweaking that command. So how cool is this? So what we can see is, whoa, so there's that crater that we looked at. That was 8 kilometers deep. In the north of the planet, I think this is the north, you've got huge mountains. These are all mountains. And in the south of the planet, you've got like a huge plain. So it's quite weird. You've got like mountains in the north, huge plain in the south. So a bit different to Earth. So let's fly around it a bit more. Now, look at... Oh, yeah. So anyway, we're flying around it. And we can see... Okay, now, what we're doing now is we're trying to maneuver this whole picture down to be a 2D image, so it's like a bird's eye map. So now it's basically that 2D image you saw before, which is quite cool. Now what we're going to do is we're going to put on that color bar. So color bar, spelt wrong, obviously. Now, yeah, this is what I mean about sometimes it looks funny. Now the color bar's gone. There we go. Right, so now we've got that colour bar back, which looks quite pretty. Yeah. Shall I tell you about it now? Yeah, so another interesting thing to see is this scale is actually in kilometres. And this is 8 kilometres, so this is 8 kilometres high here. This is 0, and this is minus 8 kilometres. So the depth between the highest mountain and the deepest valley is 16 kilometres. You just don't get that on Earth. You know, I don't know how high Everest is, but it's not 16 kilometres high. It's a really cool planet. Okay, so I think that's enough of that. Boom, presentation. Okay, so now we can do nice 3D plots from 2D data. Now, this command you will use for your coursework. This is extremely useful when you're trying to automate the loading of stuff. Very often, you'll load in a big file, and you'll be like, how big is this file? How big is this array? You can get this with the size command. So if you load in some random data from any file, just go size data, and it'll give you the size of that array. And this is actually a 1D array in itself. Right, extracting data from 2D arrays. So what coordinate do you think that point is there? Just somebody shout out. 700 and what was the one? Yeah, about that. Now imagine you want to know exactly how deep that crater was using MATLAB. So the gentleman there gave us the answer, which is very good. Imagine you want to know how deep this position, what this number was basically in the array. You could do that like this. Firstly, you load in your data, and then you just want to address that one element in that 2D array. And it's just like addressing or getting the data from a 1D array. All you do is you go, data, which is the name of the array, open round brackets. Now this is a trick. The Y position, and then the X position. So if you look at this, this is X is 700, Y equals just over 100. In MATLAB, you've got to go data, brackets, Y position, X position. I don't know why. This is because mathematicians do it backwards. I don't understand why they do it backwards. You know, if you get an OS map and you open it up and you go along the X, then up the Y, the mathematicians always do it backwards. So Y, then X. And then it will print out the depth of that crater, which is about 7.4 kilometers deep. Now, very often, we want to extract data from a huge 2D data set. And last week, we looked at extracting 1D data from a big 1D data set. So we were chopping out sounds from a 1D array. Well, we can do exactly the same trick with 2D arrays. So in MATLAB, 2D arrays are labeled from basically, are indexed from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And the same with the Y, 1, 2, 3, 4, 5, 6, 7, 8. So they all start at 1. So imagine we want to chop out the area between 9 and 13 and 3 and 5 into a smaller array that we wanted to handle and actually do some work with. We can do that in a very, very simple way. I think this is the last difficult thing I'm going to tell you. We'd literally type, so this is what we need to do to make a small array from a big 2D array. We go small array equals big array, then the start of the Y coordinate, which is 9, dot dot, end of the Y coordinate, which is 13, comma, start of the X coordinate, which is 3, end of the X coordinate, which is 5, and this will literally chop out this area here and pop it into a small new array. Okay? Any questions on that? It looks a bit theoretical there, but we're going to do an example, and it will become really obvious. So that's how we chop out little arrays from big arrays. So imagine now we wanted to just zoom in on this. I think it's a volcano there. I'm not sure. It could be a mountain. We want to zoom in on this volcano there and visualize just that mountain rather than trying to visualize this whole array. So what coordinate do you think this starts at, the X? What do you reckon? I heard the right answer there. Yeah, go on. 200, shall we say? What do you think it ends at? 250, yeah? Start there for the Y? Yeah, 300 and something, it ends maybe just over 400. So the correct answers are that. So if we want to chop this array out of this big array, all we do is this. It's very simple. We just go data equals load marsdata.dat. So we load the data file. We then go mountain. So this is the new small array we want to make, equals data. So this is the start of the y, the end of the y, the start of the x, the end of the x. And what we get is this. And you can see there's basically 14 kilometers between the depth of this valley and the peak of the mountain. So let's have a look at that and actually doing that by hand. Where's my video player? Boom. Okay, so data equals load marsdata.dat. So this is the height data. Load in the height data. Let's make a surface plot of it. And I'm again going to use this edge color command just to make it look prettier. You know, I wouldn't expect you to know that, but and this is the whole 2D array that we're interested in. Okay. Very nice. And we're interested in that mountain there that I'm just hovering my mouse over. And we'll define a new array called mountain. And then we'll just chop out the coordinates that we reckon it's at, 300.450, comma 150.250. And that's the new array. Then let's just plot that array, surf, mountain, yeah, whatever with the edge color. None, nom. Ugh. And there's our mountain. And now we can fly around our mountain, or our 2D data. Yeah. And actually, if you notice, this when I twiddle the mouse, it's going like the whole rotating of this thing is going much more smoothly because the computer's having to do less work because there's less data points in our array. So if you start having problems with the amount of data you're handling, just look at a section and visualize that rather than everything. Okay, I think there's only a couple more to go. Any burning questions on that lot? Do shout out if you... Yeah, go for it. I'm going to come up. Yeah? Tell me to stop. I went past it. Say stop. Stop. There? Forward or backwards? Yeah? That? Yeah? Oh, if you actually want to search. Yeah, if you want to search for it. So one way to do it would be you could do now is use the min command, and it would actually tell you the minimum value. But you can't yet search. We haven't yet done enough to search for particular values. That will come in about a lecture or two. Okay, it's a good question. Thank you very much. Right, I'm going to crack on now. Right, so the final thing, how long have we got? I think we've got like 4 minutes. 2 minutes. Ooh. Right, final thing is, very often you want to just take a strip of data out of a 2D array. Please don't pack up yet. You need to take a strip of data out of a 2D array. And the way you can do this is, instead of specifying basically a box, if you just set one of these coordinates just to a single number, then it will just take out a strip. So in this case, we're going from, so strip equals data 1 to 501. So that's this length here. And then this is the x coordinate of the strip. So we can literally just take out a strip of data. So this doesn't have to necessarily be a range. It can just be a value. So what we can do is we can very quickly now look at the height of the Martian land, basically, from the North Pole to the South Pole. So if we go strip, so this is this strip of data, from range y equals 1 to y equals 501 at position 700, and then plot this strip, we can actually get the height profile through this 2D data set. And we can actually see our crater there with our 8 kilometer depth. Now, what's wrong with this graph? Axes, units, title. So basically everything's wrong with this graph. Okay. Now I'll give you a tip. If you put axes and labels on every graph in your degree from now on, you'll on average get 5% more for every single lab report you do, which might just put you over that boundary from the 2-1 to the first. So labeling graphs is always a good way to get marks. That's a tip. So what we need to do, the other thing that's wrong with this array is the x-axis. So this x-axis is labeled from 0 to about 500 in data points, right? This is not kilometers, it's data points. And that's not useful for a graph. It's like array points. Who knows what an array point is? So firstly, we need to calibrate this x-axis to be in some type of useful coordinates. Guys, please don't talk. You've been talking throughout the whole lecture. Thanks. So I happen to know from Wikipedia that the distance between the South Pole and the North Pole of Mars is 10,670 kilometers. So somehow we need to recalibrate this axis from 0 to 500 to be actually from 0 to 10,000 kilometers. Now, what we've got so far is we've got our array of data basically showing the heights throughout the Martian surface. And the first element of this array holds like the value of a kilometer, then the second array value is 1.1, and it goes all the way up to the 500th element, which is, again, 1 kilometer. And you can actually see, so the data in this array is will actually look like this if you plot it out. So somehow we need to relate each one of these first, second, third, fourth, fifth, all the way up to 500th point to an actual x-coordinate, so we actually know the distance or the position where it is actually on the Martian surface. So what we need is like an array that's got actually the position of each one of these data points in it in terms of kilometers. So we need an array that goes from 0 that says this is at the South Pole, so to 20, 40, 50, 60, 80, all the way up to 10,670. So we need some type of scale array basically that holds data which tells the computer like at what x position is each one of these y points at. So what would you use, which command would you use to generate an array with a regular number that's increasing to a number that you like? Linspace, yeah? So we can just generate this with linspace. So all we do is we load the 2D data, take the strip from it, so that's just taking this big 1D strip, and then linspace generates our x-coordinate. So it's from 0, which is the South Pole, to 10,670, which is the distance to the North Pole, and with 501 points, because we know our array's got 501 points, then we just go plot x, comma, strip. So this is basically the x-axis and the y-axis, so x, comma, strip. And we get a nice graph labeled in actual kilometers rather than just some arbitrary array unit. But we're still missing x-axis, label, and title. And this is the last thing for today. So this is just something you've got to remember. If you want to put on x-axis, y-axis, and title, you need to go x label and then put in the text, y label, put in the text, and title, put in the text. And that's it. So, off to the lab. Could I please have those registers? And if anybody's been late and not signed the register, or if your mate's going to turn up to the lab now, it's going to be on the desk, the lecturer's desk of C19 in a few minutes, so you can sign in there too.